Welcome back to Math 208. This is Lecture 4, Part B. We're covering Section 4.4 in the book, Matrix Operations. At this point in time, we're going to talk about matrix product of a row column and a column vector, and then we'll talk about matrix product more generally. Okay. So in our notes, we shall see that a matrix product of a row vector. So what is a row vector? What is a column vector? Earlier, when we were showing our different types of vectors, these are column vectors. So A and B are both column vectors, and C is a row vector. Basically, it's a column with 3 rows. So it's a 3 by 1, a 3 by 1, and this is a 1 by 3. So it's where the dimensions are equal to 1. If the column is equal to 1, then it's a column vector. If the row is equal to 1, it's a row vector. So that tells you what it is. Now, how do you multiply two of these things together? And this is a rule that's defined for matrix product, and this will be extended when we talk about matrix product in general. The matrix product given, and by the way, they have to be the correct dimension. So this is a 1 by n matrix, and this is an n by 1 vector, column vector. If this dimension is not the same, then you cannot perform the operation as is not defined. So remember that the dimension, that middle dimension, has to be the same. When we have that, you take the first element, A1 times B1, and that gives you a value. Now, when we multiply these together, we're going to end up with a scalar, just a single value. And we do that because we're doing an addition here. The next is A2, B2, and so plus A2, B2, plus. We're just going to keep on going. We'll have an A3, a B3, and that gives us our next value. And then we go back and repeat until we continue this until we use up all of our values. Okay? This operation is not commutative. You can't change the order. I'm going to give an example here, and then I'm going to, as shown right here, and then I'm going to do one or two examples by hand. C times B. So C is this 4, 5, 6, and B is the column vector 4, 0, 6. Take the first 4 times 4, that's this, plus plus 5 times 0 plus 6 times 6, which gives us 16 plus 36 and is equal to 52. I'm going to do a couple more examples using row and column vectors just to make sure that we get the hang of this. This is how we expand into a matrix product in general. So we take the first term, so a 4 and a 5. Now this is, we're going to have output of just a single value. So 4 times 1 is 4 times 1 plus 5 times 2 plus 6 times 3. And that equals 4 plus 10 plus 18, which is 28, 32. Next example is A times C. So I'm reversing the order. Now I said previously that the operation was not commutative, which I indicated right here. That doesn't mean that it's not defined. It just means that they won't equal the same value. And that'll be pretty clear. Well, actually, should I do this? This is probably something I should save for a little bit later. I'm going to save this for a little bit later when we do matrix product more generally. So we'll come back to this example. And then we're going to look at A times B. So these dimensions, this is a 3 by 1, and this is also a 3 by 1. When we were talking about what is a valid operation, we indicated that these values need to be the same. So these two values need to be the same. They are not. So this is actually a not defined function. We're going to move on to matrix product, existence, and dimension. And the reason I'm going to move on to that, it'll explain a little bit more detail what was happening on those last two examples in particular. So first we're going to recall that the dimensions of a matrix are given as n by m, where n is the number of rows and m is the number of columns. In order for a matrix product to be defined, we have to have the number of columns of the first matrix equal to the number of rows in the second matrix. And I've got this color coded, and you'll see why in just a moment. When this is true, the product matrix has the dimensions of the number of rows of the first matrix by the number of columns of the second matrix. So what we're saying is that not only can we multiply row vectors and column matrix, we can multiply together matrices of various dimensions. It doesn't have to be just a single column or a single row. So from the examples, and we'll look at the A times B, which is the example that we did initially, I believe. This is the example that I indicated was not defined. So A times B. So we have that the inner dimensions, you basically just write out the dimensions. A is a 3 by 1 matrix, and B is a 3 by 1 matrix. And then we look at the inner terms. We look at the two inner numbers, the 1 and the 3. We notice that they're not equal. Because they're not equal, this operation is not defined. A times C, which is a 3 by 1 and a 1 by 3. We notice that the inner numbers are equal. So the matrix product is defined, and the dimension of the output is going to be a 3 by 3 matrix. So when we're done multiplying this, we're going to have a 3 by 3 matrix. A times D. So we have a 3 by 1 matrix and a 2 by 3 matrix. We write these out, 3 by 1, 2 by 3. We note that 1 is not equal to 2. And therefore this operation is not defined. Now if we reverse the order, we now are going to do D times A. D is a 2 by 3 matrix, and A is a 3 by 1 matrix. A 3 by 1 matrix. So the inner terms are 3 and 3, so the product exists. We can do this, and the output, our result, is going to be a 2 by 1 matrix. Now, we're going to talk about how do we actually go through the operations of calculating the product of matrices. The first thing is we always check to see if you can perform the operation. That's always the first step. So we're going to work with D and F. So D is a 2 by 3 matrix, and F is a 3 by 2 matrix. Noting that a 2 by 3 and a 3 by 2, the inner terms are equal, so we have 3 equals 3, so we can do this operation. And then we ask, what is the output going to look like? The output is the outer two numbers, which is a 2 and a 2. So we know right off that the product output is going to be a 2 by 2 matrix, which is what we're saying here. And then we can calculate each term. And we're going to start with the first term. So the first term, P11, is equal to the row vector, column vector. So we're basically doing we're basically doing this sort of an operation. We're basically doing this sort of an operation for each term. So we take the first row, 1, 2, 3, and we multiply it by the first column, and that gives us our first element in this result. 1 times 3 plus 2 times 4 plus 3 times 2 is equal to 17. Now we move on to the next location, which is this P12. And now we're going to take the result of the first row and the second column. So we have 1 times 3, 2 times 1, and 3 times 0. So 3 plus 2 plus 0, which is 5. Then we move on to the second row, and we're the first column. So this P21. So we're going to look at second row, first column. Doing our operations, 4 times 3 is 12, plus 0 plus 12 is 24. And you will get faster at this, and I probably mostly won't write it out in quite the detail that I am this time, but I think the first time we do it, and as a reference to recall, this is a good way to do it. So we're now going to find the last position, which is the P22, the second row, the second column. 4 times 3 is 12, times 0, plus 0, plus 0. So that's 12, which gives us the resultant matrix. Where do these numbers come from? 17, 5, 24, 12. 17, 5, 24, 12. Let's see what I have for other examples. So there are 2 more examples in here, in the notes. I'm not actually going to do these 2 examples. You can reference the notes. You can look them over. But instead, I'm going to do by hand. I'm going to do 2 examples. I think actually writing it out, it might be a little bit more conducive to learning it. So, D times F. Can we do this operation? I've written out the two equations. We know that D is a 2 by 3 matrix, a 2 by 3, and we know that F is a 3 by 2 matrix, 3 by 2. The threes are equal. We can do this operation. The output is going to be a 2 by 2 matrix. So we already know what size the matrix is going to be. It's going to be a 2 by 2. Now how do we go about this? We take the first row and the first column. So 1 times 3, 2 times 4, 3 times 2. That's addition. That's for this position. I'm going to break this up into quadrants like this. I'm going to look at this position, which is the first row, the second column. So that's 1 times 3 plus 2 times 1 plus 3 times 0. Going down to the next quadrant, for position, the row is the second row, the column is the first column. So it's 4 times 3, which is 12, plus 0, plus 6 times 2, which is 12. And finally, the second row, the second column, which is 4 times 3, 12, plus 0, plus 0. Adding everything up in here, we end up with 14, 17, 5, 24, and 12. I didn't realize this is the example I had already done. I apologize for redoing that example. So I literally just did this example again. I'm sorry for that. Okay. Anyways, we're going to move on. This is equivalent to, so if we have a matrix, if you'll notice, looking at this matrix, we've got 2, 4, minus 2, minus 1. 2, 4, minus 2, minus 1. So this is basically taking this matrix and squaring it. You're multiplying it by itself, which is the equivalent to square. We can certainly do that. This is a 2 by 2 and a 2 by 2. The inner terms are 2 and 2. We know we can do the operation. The output is going to be a 2 by 2. Okay? So let's go ahead and do the calculations on this. The first row, first column, 2 times 2 is 4, plus 4 times minus 2, which is minus 8. First row, second column, 2 times 4 is 8. 4 times minus 1 is minus 4. Second row, first column, minus 2 times 2 is minus 4. Minus 2 times minus 2 is plus 4. Second row, second column, minus 2 times 4 is minus 8. Minus 1 times minus 1 is 1. I'm going to back up 1 point. I made a mistake here. I apologize. This is not a 2. Let's do this calculation over. So minus 4, minus 2 times 2 is minus 4. Minus 1 times minus 2 is 2. And this equals minus 4, 4, minus 2, and minus 7. There's a couple things that we can say about matrix multiplication and matrix product. Actually, I think I should do the E times D. I think that's an important example to do, so I'm going to do that right away. Which is the example that is being shown right here. I'm going to do this one by hand real quick. We can do it. It'll give us a 3 by 3 output matrix. One of the reasons I'm going to do this one, it'll indicate and it'll show very clearly that the order in which you put the matrices matters. You can't just put it in whatever order you want. It has to go in a very certain order. It has to go in the order it was given if you want to do any multiplication whatsoever with them. 1, 4, 2, 0, 3, 6. So our output is going to be, well, let's do the calculations here. This is a 3 by 2, and this is a 2 by 3. We can do the operations, a 2 and a 2. The output is going to be a 3 by 3. So the output of this is going to be a 3 by 3. I'm going to refer back to the notes real quick. The output of E times D is a 3 by 3 matrix. The output of D times E is a 2 by 2 matrix. So clearly D times E does not equal E times D. They're two totally different things. And it's very important to keep that in mind when you're doing operations with matrices. But let's go ahead and do this operation. I'm going to start to do it a little bit faster. First row, first column, 2 plus 4. First row, second column, 2 plus 0. First row, third column, 6 plus 6. So let's review. 2 times 1 is 2. 1 times 4 is 4. 2 times 2 is 4. It's always a good idea to double check some things. 2 times 2 is 4. It's easy to make mistakes, so try not to. 2 times 2 is 4. 1 times 0 is 0. 2 times 3 is 6. 1 times 6 is 6. Second row. 1 times 1 is 1 plus 2 times 4 is 8. 1 times 2 is 2 plus 0. And then 1 times 3 is 3 plus 2 times 6 is 12. And finally the last row. 3 times 1 is 3 plus 16. 3 plus 2 is 6 plus 0. And 9 plus 24. 9 plus 24. Simplifying this, we have 6, 9, 19, 4, 2, 6, and 12, 15, 33. We've only got a couple more comments, just a little bit more on this session. So a couple more comments. First of all, we have to assume that the operation is defined. We always check to make sure the operation is defined. But assuming that it is, matrix products are not commutative. As shown above, d times e does not equal e times d in this case. It is possible that they will. There are some matrices in which they do, but you cannot guarantee that. Matrix products, however, are associative, meaning you can change the order of the parentheses, and they're also distributive over addition. So d times e plus f is equal to d times e plus d times f. In summary, always verify that the matrix operation is defined. You can also determine the dimensions of your result matrix. And do this before you do any calculations whatsoever. Take your time performing the operations. It's row to column, but take your time doing it. And then there's some homework problems on page 220-21, problems number 33 to 48. Make an effort to do all of those. They'll help you have a better understanding of how to work with these, especially in commutative, associative, distributive, how to add them together, whether the operations are defined, etc. And recall, when we say a squared, or any matrix squared, it's just the matrix times itself. So a to the 10th is the matrix times itself 10 times. Now you can only do that with a square matrix. That concludes lecture number 4.